Karst topography, flow of underground water and work, solution, erosion and deposition landforms. Karst landforms are produced by the geomorphic agent such as underground water. The term karst is related to limestone. The basic question here is that do the karst landscape is evolved everywhere where there is a presence of underground water. Any limestone, that is calcium carbonate, and dolomite, that is magnesium carbonates region, showing the typical landforms produced by the action of underground water through the process of solution and deposition are called as karst topography. Karst topography is typically developed in the karst region of Yugoslavia situated along the eastern margin of Adriatic Sea. The word karst is a comprehensive term applied to limestone and dolomite areas that possesses a topography peculiar to and dependent upon the underground water and the diversion of surface water into underground route. The term karst comes from the limestone region in Yugoslavia and some areas bordering the Adriatic Sea. With this background, the main aims of this lesson are to understand the flow mechanism of underground water, to know the work of underground water, to bring out the factors essential for the development of karst landscape, to study various depositional landforms evolved by the underground water. The underground water does not flow like a river. The flow of river water is measured in meters per second, but the flow of underground water is so slow that it is measured in meters per day or per year. The factors responsible for the slow motion of the underground water are 1. Porosity of the rock and 2. Permeability of the rocks. Porosity of the rocks. The amount of water that has been locked up into the rocks depends upon the porosity of the rock. The ratio of total volume of the open spaces in the rocks to the total volume of the rocks is called as porosity. The porosity of the sand and gravel ranges from 25 to 45%, but the porosity of granite is hardly 1%. The porosity of rock depends on size, arrangement, closeness and compaction. The seeping water dissolves the salts present in the rock and increases their porosity. Permeability of the rocks. When the water flows through the rocks, some rocks allow more water than the others. The capacity of the rocks to transmit water through them is called as permeability of the rocks. The presence of pores in the rocks is not only the factor transmitting the water. Joints, fissures present in the rocks are also responsible for transmitting water. A rock may not be permeable, though it may be porous. The fine pores, as in case of clay, are of great hindrance to the flow of water. Igneous rock like granite and basalt limit the flow of water. The surface water percolates well when the rocks are permeable. After vertically going down to some depth, the water underground flows horizontally. It is this downward and the horizontal movement of the water which causes rocks to erode. Initially, water follows the surface drainage and the surface water moves through the joints and slowly converts into the form of underground water. The work of underground water is exceedingly slow because of its very slow rate of movement. The work of underground water includes chemical erosion of the soluble rocks at the surface by the surface water and below the surface by percolating and moving underground water. Limited transport of eroded materials is in the form of suspended and deposition of solutes. The rate of flow of underground water is very slow. Hence, the transportation and erosion by underground water is not that important. As the movement of underground water is very slow, it cannot transport the enough material. As a result, chemical erosion and deposition go together. The work of underground water includes only that part of the chemical erosion of carbonate rocks at the ground surface. Ground surface is included, which is related to the percolation or infiltration of rainwater. Underground erosion starts with water percolating through the joints, faults and dissolving the soluble rocks. Water table is able to undertake erosion only by dissolving soluble rocks such as limestone and dolomite. The erosional work is mostly in the form of corrosion or solution. Solution activity. The main source of underground water is rainfall. Normally, water cannot dissolve the limestone rock. The rainwater, while passing through the atmosphere, dissolves carbon dioxide present in the air. The rainwater, which has carbon dioxide dissolved, becomes weak acidic in nature and turns into diluted carbonic acid, which can dissolve the rock like limestone. Rainwater mixed with atmospheric carbon dioxide becomes active solvent agent and dissolves the carbonate rocks at the surface and below the surface to form various solutional landforms. When the rainwater is mixed with atmospheric carbon dioxide, it forms a weak acid called as carbonic acid. The slow moving underground water can dissolve huge quantities of soluble rocks and carry them away in solution. Karst topography develops in those areas where thick beds of massive limestone lie just below the layer surface. Besides, karst topography also develops on dolomite and chalks. Typical karst region is seen on the Adriatic coast of Yugoslavia. Karst topography is well developed in southern France, Spanish Andalusia, northern Puerto Rico, western Cuba, Jamaica, southern Indiana, central Florida of USA. In addition to these areas, there are innumerable areas where karst features are present but do not dominate the landscape. The chalk region of England and France are few examples of such areas which exhibits some karst features. None of the above mentioned areas displays all the possible karst landforms. The reasons behind varying conditions of lithology structure, height of the water table and climate. This is well illustrated by some of the significant differences between tropical karst and that of the mid-latitudes. Actually, full development of the karst landscape is restricted to relatively small number of locations. The conditions that favor the development of karst topography are: 1. Presence of limestone at or near the surface. The limestone must be massive, thickly bedded, hard and cemented, well jointed. Most of the notable karst areas are in the regions where limestone underlies the surface. Second reason, limestone must be non-porous and thickly bedded, dense, so that water will infiltrate through the joints, resulting into effective corrosion of the limestone along the joints. Permeability, as permitted by numerous joints and bedding planes, is favorable. The third reason being The limestone should be widely distributed in both aerial as well as vertical dimensions. Fourthly, the carbonate rocks should be very close to the ground surface so that rainwater may easily and quickly infiltrate into the beds of the limestone and may dissolve the rock to form solutional features. The fifth reason is that there should be enough or moderate rainfall so that required amount of water is available to dissolve the carbonate rocks. In general, arid and semi-arid regions do not exhibit marked development of karst landforms. These favorable factors give rise to erosion and deposition, which in turn gives rise to distinctive type of karst landforms. Karst topography is characterized by both depositional landforms and solutional landforms. As the solution of carbonate rocks by the underground water continues, the underground water receives more and more solutes and becomes saturated with sediments. Since the movement of groundwater is exceedingly slow, it cannot transport materials, thus chemical erosion and deposition go together. After the limestone caves are formed, the water charged with limestone that seeps through the walls and roof of the roofs the deposits of calcium carbonate. The calcium carbonate is deposited when the water carrying in it the solution evaporates as it trickles through the rough surface. Reduction in the pressure. Third factor is loss of gases like carbon dioxide. The deficiency of carbon dioxide decreases the solution process and thus is helpful in the deposition process. The deposition of these sediments mostly takes place in various places and various forms in the underground cave, such as the floors of the cave, along the ceilings of the cave and in the joints. After the underground caverns are formed, the water seeping through the walls or the roofs of the cave deposits calcium carbonate in the form of various features. An underground cavern exhibits a variety of depositional features which add to their beauty. The most striking features are usually accumulations of calcium carbonate on the ceiling, walls and floors. Cave travertine is an inclusive term generally applied to many banded calcareous deposits which are called as travertine, whereas the calcareous deposits softer than travertine at the mouth of the caves are called as tufa or kalk tufa. According to some scholars, these forms are called as speleotherms, in which calcite is the common constituents. All type of deposits in the underground cavern are collectively called as speleotherms. Davis in 1930 suggested that the term dripstone be used to include all the depositional forms developed by the water dripping from the underground cavern ceiling. The calcareous deposits from the dripping of water in dry caves are called as dripstones. The depositional features in the karst areas which are associated with the underground caves are 1. Stalactites, 2. Stalagmites, 3. Pillars and 4th drapes or curtains. Stalactites are the columnar limestone deposits that hang from the roof of the underground caverns. Stalactites hang from the ceiling of the underground cave as icicles of different diameters. Stalactites are formed due to the deposition of calcareous solutes which are carried by the water dripping through the cave ceilings in the dry environment. The water is evaporated and the solutes are deposited in icicles or needle form. Normally they are broad at their bases, that is near the roof of the cave, and they tapers the free end towards the floor of the cave. The deposited material hang from the ceiling of the roof of the limestone cave by the percolating groundwater called as stalactites. The stalactites hanging downward are almost perpendicular to the cave ceiling. The shapes of the stalactites are controlled by the shape of the cave ceiling. Stalactites become uniform and tapering ends are directly pointed towards the cave floor. When the cave ceiling is flat, uniformly arched, as the water enters the cave, part of it evaporates and small amount of calcium carbonate is left behind. A stalactite forms as water charged with calcium carbonate in solution seeps through the roof of the cave drop after drop from the ceiling and then falls on the floor. The dripstones or the deposit growing sidewards from the stalactites are called as helictites. The helictites of globular structure are called as globulites. Stalagmites are the columnar deposits which grows upward from the floor of the underground cave. It is formed from the precipitation or deposition of carbonates in calcite form. A stalagmite grows upward from the floor of the cave. The solution that drops from the cave floor is also precipitate and crystallized and forms a column-like structure of stalagmites. The stalagmites are formed when the water charged with calcium carbonate in solution seeps through the cave roof drop by drop and falls on the floor of the cave. The calcareous column of dripstones growing upward from the cave floor are known as stalagmites. The deposits growing sideward from the stalagmites are called as heligmites. Cave pillars are formed when stalactites and stalagmites join together. When stalagmites from below and stalactites from above develop towards each other and combine to form a pillar, such pillars are called as cavern pillars. A typical example of pillars is seen in the Carlsbad caves of New Mexico in USA. Sometimes stalactites developing gradually extends to the floor and turn into pillars. Water percolating from the fractures in the roof of the underground cave may not form a thin vertical sheet of deposits, drapes or curtains. Water percolating from the fracture in the roof of the underground cave may form a thin vertical sheet of deposits known as drapes or curtains. They are very thin wavy dripstones hanging from the cave ceiling. Drapes or curtains are formed in caves where rivulet of underground water flows along the inclined roof. The curtain attached to the ceiling of the cave hangs downward. The conversion of surface water into the form of underground water in the karst or limestone region is very slow. The flow of underground water depends upon the porosity and permeability of the rocks. The work of underground water is exceedingly slow because of the slow rate of its movement. The work of underground water is in the form of erosion and deposition. The erosional work of the underground water is undertaken through the mechanism in the form of corrosion and solution. The solution activity mostly takes place when the rainwater is mixed with atmospheric carbon dioxide to form carbonic acid, which takes the rock like limestone in solution. The transportation work of the underground water is minimal due to its slow movement. The deposition features in the karst landform is mostly restricted to the underground cavern. The major depositional landforms include stalactites and stalagmites, pillars and drapes or curtains. The stalactites and stalagmites and pillars are the most interesting features of the cavern.